If you can open the workbook, we are on page 1 or page, yeah. All right. I'm going to go through the theory quite quickly because you guys know this stuff, and it's more about the practice of the theory. Okay, the first thing is what probability is. It's just a measure of likelihood. Okay, and we come across probability in our lives all the time. There's a 50% chance that it's going to rain. There's a 70% chance that this person's going to win. We understand probability. We actually are, as human beings, we are wired for probability. We know it. Okay, all right. Probabilities always range between 0 and 1. And I'm going to write stuff down here, and you must choose whether you want to write it or not. If you know it and you don't think you need to write it, that's absolutely fine. 0 means impossible, can't happen. Okay? And 1 means guaranteed. It's definitely going to happen. And every probability answer lies somewhere between those two numbers. Okay, the closer to 1, the more likely it is to happen. Okay, we have a thing called the sample space, and what the sample space is it's a set of all the possible things that can happen. Okay. Probabilities are normally expressed as percentages. Okay, I like to think of a percentage as the SI unit. Those of you who do science, who teach science, the SI unit of fractions. We don't hear on the weather forecast, there's a 17 out of 28% chance of rain. 17 out of 28 chance of rain tomorrow. We don't hear that, am I right? And we don't hear that the price of a share increased by 5/11. We don't talk like that. We talk in percentages. Percentages are globally understood fractions. Okay, right. So we often give our answers as fractions. Okay, and the probability of an event happening is just this formula here. Now, in the workbook here, you'll see some of the colors are a little bit funny. I've put in blue on my sheet here the formulas that get provided in the exam. In red, I've put the formulas that don't get provided, but that your learners definitely need to know. What we're going to give you at the end of today's lesson is a thing called a Maths Mate. All right, it's a little book, and in that little book is it's the same stuff, but for the whole matric syllabus, and that book is printed in color. So you will have the red and the blue for this topic in that book. Okay. The handout you've got today in front of you is in black and white. Okay. This formula here gets provided, but to be honest, it's not the most useful formula because it's fairly obvious. Okay. If I throw a die, okay, and I think you all know that a die just has got 6 faces. What's the probability that I get an even number? And I want you guys to participate. This is a lesson, okay? 50%, 1 over 2. It's both of those things. Before it's simplified, it is 3 out of 6. 6 is the number of things in the sample space. When you toss a die, 1 die, 2 dice, okay, that's been misused so often now that most people just call everything a dice. They'll talk about 1 dice, but anyway, all right. That's how many things that can happen, 6. How many of those 6 things that can happen are even? 2, 4, and 6. So 3. This is the number of ways we can get an even. So it's 3 out of 6. That formula is given. It's not very useful. Now there's another concept, and that's called the complement. Okay, the complement is the balance of the probability. We sometimes use a line on top of it like that, or sometimes we use a little like a dash. Okay, and that's the balance of something. It's the probability that it doesn't happen. If there's a 30% chance of rain, what's the probability that it doesn't rain? 70%. Okay, because probabilities and their complements always add to 1. That formula is not given. Okay, so I'll give another example. If there's a 20% chance let's just think. If there's a 20% chance that my favorite tennis player is going to win the next tournament, what's the chance that he doesn't win? 80%. Okay, all right. Those two things add up to 1 or to 100%. This is a very, very important idea. The complement of at least 1 is none. The best way of explaining that is with some examples, and we'll get to those. Okay. Now, There are two very big ideas in probability, and they are seriously important. Ebalulekile. Okay. The first one is this idea of independence, things being independent of one another. If I throw a dice or a die and I toss a coin, those two things are independent of one another. What happens here does not affect what happens here on the coin. Okay, independent. All right. If, for example, I've got a bag of some chocolates, maybe. Is there a bag of chocolates? Yeah, there's a bag of chocolates, as luck would have it. Okay, and there are different types of chocolates in here. And I take out a chocolate and I eat it. And then I take out a second chocolate. Those things are dependent because the chocolate that I take out the first time will influence what type of, it will influence the probability of what I might get the second time. Now, this is a very, very big idea. If two things are independent, then the probability that they both happen, A and B, and I've used the symbol and the word, is equal to the product of the probabilities that they each happen. And we'll do some examples of this, okay? So at the moment, this is a little bit like, maybe like trying to drink from a fire hose, because I'm just giving you all the theory, but this is a very, very big idea. Now, this arrow has got two heads on it. It goes both ways. So if they're independent, then we can calculate the probability that they both happen by multiplying the two probabilities. But the other way around as well, if this bottom line is true, then the top line is true. And because of that, we can use this idea to test whether events are independent or not. Okay, the next thing is the idea of things being mutually exclusive. Mutually exclusive things cannot both happen. For example, a learner being in grade 10 and a learner being in grade 12. Cannot happen. Okay, ayikho le nto. All right, non-mutually exclusive things can both happen. For example, a learner being a female and in grade 12. You've almost certainly got one in your school. Have you got a grade 12 female learner in your school? Yes, you have. So it's possible. Okay. All right. Exactly the same idea, double-headed arrow. When things are mutually exclusive, the probability that they both happen is 0. So, for example, the probability of a learner being in grade 10 and in grade 12, 0. Okay. And the arrow's got heads on both ends, so we can also go from the bottom line to the top line. If the probability of A and B is 0, then they are mutually exclusive. Okay, right. Then the last formula, last probability formula that we need to worry about here is this one, and this one gets given to you. And what it says is that the probability of A or B, we add the probabilities, and then we subtract the probabilities that they both happen. Okay, now we're going to explain why this formula works and why it's important. This is the single most important formula, I think, all right? It does get provided. That's why it's written in blue pen here, blue ink here, and in the MathsMate that we're going to give you. Okay, we're going to practice using them just now. Two ideas now. Probability trees. These are just tools that we use for probability. Probability trees and Venn diagrams. Okay, so let's look at this now. A probability tree is useful for working out what we call compound events, when more than one thing happens. Okay, so let's just read this and see if we can do this together. A bag contains 3 red beads, all right, and 1 green bead. So now what we're going to do, we're going to take out a bead, all right, and then we're going to look at it. We're not going to put it back. We're going to then shake the bag and take out another bead. Okay, what's the probability that my first bead is red? How many beads are in the bag? 4. How many of them are red? 3. Guys, what you've just used there, you've just used this formula. Am I right? Okay. All right. What's the probability that it's a green bead? It's 1/4. Now, a really important idea is that whenever the branch splits, the probabilities of all the choices must add to 1. Okay. Right. Now, we've taken a red, on the top branch here, we've taken a red bead out. What's the probability that I get another red bead? 2 out of 3. Well done, because we've taken a bead out, so there's now only 3 beads left, and the bead we took out was red. Does it make sense? It always makes sense. Izibalo zikaqeke injalo. Okay, you know this. Okay. What's the probability of a green bead? 1/3, because remember the green bead is still in there, but there are only 3 beads there. If we took a green bead out the first time, what's the probability of now getting a red bead? 3 out of 3. It's definite. Okay. What's the probability of getting another green bead? 0. It's actually 0 out of 3, but it's 0. Okay. Now, if we want to work out the probability of one of these compound events, in other words, a red followed by a red, what we do is we multiply these fractions down the line. So 3/4 times 2/3 happens to be 6/12. Okay? I'm going to leave it as 12ths. 3/4 times 1/3, 3/12. And 1/4 times 3/3, 3/12. Not surprisingly, okay, the last one's 0. 0/12, okay? Not surprisingly, these add to 12/12, they add to 1. That's all the things that can happen. So, but now if we say to you, what's the probability that we get one of each in this diagram? Let's just look at our diagram here. Where do I get one of each? Which branches? This one, red, then green. Norma? Green, then red. Okay, those 2 branches. So in fact, the probability of getting one of each color, I must now add these 2 things. Okay, it will be 3/12 plus 3/12. It will be 6/12. Okay, 6/12 is the same as a half. All right, 50%. Okay. The next thing that we need to be comfortable with is the idea of Venn diagrams. Okay, and when we draw one of these, the big idea here is to start in the middle, in the intersection, and to work outwards. So, suppose these probabilities exist. The probability that someone likes tea is 40%. The probability that someone likes coffee is 65%. The probability that someone likes tea and coffee is 30%. Can we draw this Venn diagram? Where should I start? You just put your hand up and say, yes. In the middle. And what am I going to put here? I'm going to put 30%. Okay. Right. Now, can you tell me what I should do next? Okay. 100%. Correct. Okay. Guys, 40% of people like tea. But of those 40%, 30% are already in there. So 40 minus 30, that's going to give us 10%. Okay? All right? Now, what about, how will I work out what's going to go here? 65 minus 30, 35%. Okay, now, if we add these up, we've got 40 and 35, we've got 75. What are we missing? Those who don't like either. And what percentage are those? Those are 25%. All right, now I want to spend just a little bit of time on this, okay? Because this diagram really helps us understand a whole lot of stuff, okay? The first question now, are these events independent, liking tea and liking coffee, okay? And how are we going to check that? What we're going to do, I'm just going to remind you up here, we're going to check if the probability of both is the same as the product of the probabilities. Okay, so let's check that. The probability of both tea and coffee is 0.3. That's 30%. The probability of tea, and I'll tell you, you need to be aware of this as a teacher, because where your learners are going to go wrong, a lot of them are going to say, oh, the probability of tea is 10%. The probability of tea is not 10%. The probability of tea and not coffee is 10%, but the probability of tea is 40%, okay? And the probability of coffee is 65%. So now what we're going to work out here is we're going to work out that product, 0.4 times 0.65. Now that comes to 0.26. All right, are they the same? No. Because they're not the same, these events are not independent. Okay. In other words, there's some sort of connection or relationship between them. Are they mutually exclusive? And who can tell me quickly, are they mutually exclusive? No, they're not. Why not? Yeah, the probability of both of them is not 0. Okay, so no. The probability of tea and coffee is not equal to 0. Okay, Right, now the last thing I want to just dwell on this diagram, and I didn't write it at the bottom of the page, but I want to show you where the probability of tea or coffee formula comes from. Tea or coffee. Okay, what we're going to let's just check which areas we want to count. Do these 10%, do they like tea or coffee? Must we tick that? Is that true? Yes. Do these people like either tea or coffee? Yes. And this is a very important idea, because I think a lot of the problems come in with second language speaking, but the word or means both. It includes both. And I'm going to give you an example. Okay, Ruth and I we're brothers and sisters, but when we were little, if my mother, or when we were teenagers, if our mother said to us, Ruth, you can go out with your friends if you've tidied your bedroom, because it was never tidy, okay? All right? If you've tidied your bedroom, or if you've washed the dishes. So if she's tidied her bedroom, can she go? Yes. If she's washed the dishes, can she go? Yes. If she's tidied her bedroom and washed the dishes, can she go? Yes. Okay. So we count both of them in the or. All right. There, we must count those and we must count those. Now let's look at the formula for tea or coffee. I'm just going to remind you. What we do is we add both the probabilities and then we subtract that. Now have a look here. When we add the probability of tea, do you agree that I'm counting everything inside this red circle? Okay? And when we add the probability of coffee, I'm counting everything inside this green circle. Okay. Can we see why this is not going to be correct? What am I doing? I'm counting that middle piece twice. So what must I do? I must subtract the probability of tea and coffee. Does it make sense? It always makes sense. There's not a single piece of mathematics that does not make sense. It always makes sense. Right, now, we're getting on to the more interesting part, which is counting techniques. Okay. And so what I've got with me here today is I've got some izikogo and some, what do you call these things? I do know izibugo, I think. Okay. All right. So I'm going to lose these ones. Okay. But so what I've got is I've got two different pairs of sunglasses. I've got these ones. Quite cool. Am I right? Very cool or quite cool? Very cool. Okay. All right. And then I've got these ones. Okay. Maybe not so cool. All right. And then I've also got three hats. I've got this one, this red one. Okay. I've got this blue one. And then I've got this one. And when I go fishing, this is the one that I'll wear. Okay. All right. And I think it makes the fish scared. Okay. All right. Okay. Now, how many different combinations of these can I wear? All right. And what I want you to do is I just want you to write them down. So we've got, you can call them, it doesn't really matter, but just write down the sort of options that we've got. Here's an option, okay? These sunglasses with that hat. That's one. All right. I could create other options. I could maybe do this. There's another option. All right. Or maybe I could do this. There's another option. I want you to write down all the options. You can give them whatever names you like. All right. Maybe you want to call this blue, red, and hat. Okay, or H for hat. And maybe you want to call these sunglasses red and these ones black. So for example, you might write down R and B. What that represents is the red glasses, these ones with the red on the side, and B, the blue hat. Okay. I'm asking people to give me some options here. What options have we got? Okay, tell me, I just want some options. Tell me, and then if we're missing any, can anyone give me another option here? The red sunglasses with the red hat. Red sunglasses with the hat. The black or blue, yeah. With the blue hat. With the red cap, sorry, yeah. And then lastly, the black sunglasses with the hat. Are there any that we are missing? No. There are only 6. Okay? All right. And what we're going to look at here is how many choices are there for the glasses? There's 2. And with each of those choices, there are 3 choices for the headwear, okay, for the hat. Okay, and so the final answer is 6. Right, we're going to look at lots of different scenarios, but before we do that, what if we also had a choice of 2 scarves? How many combinations would we now then have? So remember, we've got 6 different combinations. Here's one combination. Blue, this, and these sunglasses. Now, I've got 2 different scarves. So I can either wear, maybe the scarves are green and yellow. Okay, what's that going to do to the total number? It's going to change it by, what's it going to do? Is it going to? It's going to multiply it by 2. We would have 12. And that 12 would be 6 times 2. Because every single combination can now happen with the green scarf or the yellow scarf. I don't have any scarves, which is why I didn't bring any. Okay, all right, now, there's a thing called the fundamental counting principle. And what it says is that we just multiply numbers of choices. But I want to ask you this question as well. What if I decide with these outfits, leave the scarves, just the glasses and the hats. What if I decide I don't have to wear a hat or glasses? What's that going to do to my number of choices? And we'll write them down again. I could have no glasses, and then I could have the blue hat, the blue, the red, or the hat. Okay? Is everyone okay with that? What else could I have? I could have the black glasses with the blue, the red, or the hat. What other options have I got? I could have the red glasses with the blue, the red, or the hat. Where's the mouse gone? Okay, and what other options have I got? This is, what have I done here? Black, okay, red glasses, blue, red, hat. Red glasses. What else can I have? I could have no hat, okay? And I could either have no hat with the black glasses or the red glasses. How many are there now altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. What am I missing? Oh, no hat, no glasses. Ha, hala, la. Okay, thank you. No hat, no glasses. Thanks, Mavis. Yeah. Thankfully, someone in the room is wide awake and concentrating. Yeah, guys, there are 12 options now. Now, the reason I've put the idea of not wearing glasses and hat is because it allows us to calculate something which is quite interesting, which we'll get back to just now. Let's look at another scenario, okay? And I want you just to try and complete this quickly. We've got from town A to town B, there are 5 roads. From B to C, there are 2 roads. And from C to D, there are 3 roads. How many ways can I get from A to D? And you can just put your hand up and you can tell me if you know. What's the total number of different ways I can go from A to D? Just if you want to answer, just put your hand up. I might even have a chocolate for you. Ruth will give it to you. Yes. You've said 30. Okay. Can you tell me how you got 30? All right. So guys, I think 30 is good, but why? You multiply them. And the reason you multiply them is because any one of these can go with any one of the routes from B to C. And so if we just from A, thanks Ruth, from A to C, there would be 10, all right? And guys, we can if we numbered these roads, if your learners are not confident about this, you could number the roads. You could go 1, 2, 3, 4, 5, 6, 7. So if we just go from A to C, I'm going to tell you that there are actually 10 options, because we could go 1, 6, 1 then 6, we could go 2 then 6, we could go 3 then 6, we could go 4 then 6, we could go 5 then 6. Or we could go with each of those and then go with 7. 1, 7, 2, 7, 2, 7, 3, 7, 4, 7, 5, 7, and 6, 7. 4, 7, and sorry, not 6, 7, 5, 7. Okay, and there's our 10. Okay, 100%. Here, we're now at a restaurant, okay? And this restaurant has got 3 choices of starters. You can have this delicious prawn cocktail, you can have soup, or you can have salad if you're feeling very healthy, okay? The main courses, less healthy. There's a curry and rice, there's a steak and chips, there's a fish and chips, and there's a burger and chips. The puddings, there's only 2. You can either have this waffle, or you can have ice cream and chocolate sauce, okay? How many different meals are possible? Different meals. 24. 3 times 4 times 2. All right. Now, I want you to quickly work out for me what, quite often, when people go for supper, they say, we're not going to have all 3 courses. We're just going to have 2 courses. Okay? Now, we're going to say that you've got to have the 2 courses in standard order. In other words, you're not going to start with a pudding. Okay? You can either have a main course and then a pudding, or you could have a starter and then a pudding. Okay? That's what my wife quite often likes to have, a starter and then a pudding. Okay, I like to have all 3, but you can see I like to have all 3. Okay, all right. So, if we only have 2 of the 3 courses, I want you to tell me how many meals are now possible at this restaurant. Okay, and we need to think about different cases here. And I've given you a bit of a framework to work it out. Yes, Nonhlanhla. 26 meals. Nonhlanhla is saying 26. Before Ruth gives her chocolate, let's just ask her how she did that. Okay. If we don't have a starter, Nonhlanhla, how many do you have? 4 times 2, which is 8. There are 8 possibilities if you don't have the starter. If you don't have the main course, Nonhlanhla, how many options are there? 3 times 2, which is 6. And if you don't have the pudding, how many options are there? 3 times 4, which is 12. When I last checked, 8 plus 6 plus 12 was 26. Halala. All right. Uyinqobile. Okay. All right. Pendula ikasi. Turn over the page. All right. Now, when Ruth and I don't know if she will remember this, but when Ruth and I were little children, our father used to do the crossword in the Sunday Tribune every week. And this crossword was very interesting because it was very, very easy. The clues were very easy. All right. So I'm just giving you 2 clues here, okay? It says a something can be considered a nuisance, okay? And it's something A, something T. Anybody think of some English words that might be a nuisance? A cat. A cat might be a nuisance. What else? A bat. Yeah, a bat might definitely be a nuisance. Anything else? A hat. I don't think a hat will be a nuisance. Maybe it will. Igundan? A rat. I think a rat might definitely be a nuisance. Okay. So, now, something is considered a good score in a certain sport. Okay. Now, this maybe you might or might not know this. Yeah, but 10 definitely, if you're doing gymnastics, a 10 is a very good score. If you are playing cricket, a ton is what we call 100. Okay, so a ton would be a very good score. So, how many different ways can we fill this crossword in? Just this crossword, just with 2 clues. 6, absolutely, because we've got a choice, Singaketa, we've got a choice of 3 for this clue, but we've got a choice of 2 for this clue. Okay, so there's 6 ways of filling it in. Now, our father used to fill in this thing, but it had like 25 clues. But every clue had at least 2 choices. And he had to pay 1 rand for each entry. Okay, so every time he entered the crossword, he had to 1 rand. Okay, the prize was 1,000,000 rand. So you think, oh, it's quite easy, I'm going to fill this thing in. But because there are 25 clues, and there's 2 choices for every clue, all right, the final number of ways you can fill this thing in is 2 to the power of 25. Let's look at what 2 to the power of 25 is. All right? So if he wanted to be absolutely, okay, I calculated earlier with 2 to the power of 24, still on my calculator. All right, it's 33 million. There are 33 million different ways that you can fill the big crossword in. Not the one with 2 clues, but the one with 25 clues. Okay, so it grows quickly. Our father used to try every week, and he never won. Okay, all right, and it shouldn't surprise you that he never won. Okay, now, this for me is a really nice application of counting techniques. How many factors does a number have? Okay, a certain number. We've chosen 24 here, but this method will work for any number. And we should be able to understand why it works. All right, if we prime factorize 24, so we break it into its building blocks, just using prime numbers. 24 is made up of 3 2s multiplying together, and then 1 3. When we look at this number, will 5 go into this number? No, obviously not. Will 3 go into this number? Yes. Will 3 squared go into this number? No. So the only things that will go into 24, the only things that can be a factor of 24 must be made up of 3s and 2s. But we can't have more than 3 2s, and we can't have more than 1 3. But we can have no 3s. I'm going to give you an example of a factor of 24. Do you agree that that number here will be a factor of 24? What is that number actually? It's 4, it's not 12. 4 times 3 to the naught, it's just 4. Okay. Is 4 a factor of 24? Yes. Every single factor of 24 will have some 2s, all right, and some 3s. How many choices have we got for the number of 2s? There's actually 4. And the reason there's 4, why are there 4? Because of 0. We could have no 2s. We could have 1 2, we could have 2 2s, we could have 3 2s. We can't have 4 2s because that wouldn't be a factor. How many choices have I got for my 3s? 2, all right? And so, in fact, there must be 8 possible choices. 4 times 2, 8. There will be 8 factors of 24. And if you look at the bottom of your page, upside down, there they are. They're written there. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8. Those are all the factors of 24. You can work out how many factors any number has once you've prime factorized it. All you do is you add 1 to each of the powers, and you multiply those numbers. And the reason you're adding 1 to each of the powers is because of the possibility of 0. Okay. All right, so 24 has got 8 factors. All right. We've just got these new number plates in KwaZulu-Natal. I don't like them, okay? I don't like them because I used to, especially when I'm away from home, and sometimes we go up to the Kruger Game Reserve and we're driving there and we see an NR car. We stop and we chat, even if we don't know the people. We stop because we might know them, okay? All right, now we see CS, my one now, CS02XMZN. All we know is that the person's from KwaZulu-Natal, okay? The only thing I do like about these number plates, and we spoke to your learners at the beginning of the year, is you can add them, you can multiply them, and you can prime factorize them. 2 squared times 3. Okay, and that's just a good exercise to get into. As you drive along, don't have an accident, but just add them, multiply them, prime factorize them. Okay, right, now, the reason these number plates came in, okay, is because in some areas, like where Ruth lives in Umhlanga, okay, they were running out of numbers. When Ruth and I were growing up, there was just ND. It was Durban, it was Westfield, it's everything. Then they said, oh, no, we're running out. Then they made NPN, which is Pinetown, okay? And then they made NUR, Umhlanga Rocks, and that was Ruth's number plate, Umhlanga Rocks. But then they were running out of numbers for places which were very full of people. So then they said, no, we're going to just scrap this thing and we're just going to go to this. How many number plates are possible now with this new system? And I haven't seen the rules, but I have never seen any vowels here in these letters. Okay, so I'm assuming that we're not using vowels. You know what the vowels are? A, E, I, O, and U. Okay, so we can't use those. A, E, I, O, and U. But we can repeat digits. You can see here we've got BB. Okay, so we're going to multiply a number of choices. Maybe someone, if you've got a calculator, you can tell me, I know what this answer is. If someone wants to work it out for a chocolate, how many different number plates can we have? Anyone got an answer for me? For the total. Guys, it's 19,448,100. And where that comes from is a choice of 21, not 26. 21, because we can't use these ones. Then 21 again, then 10. 10. Don't say 9, because we could go from 0 to 9. Okay. What I want you to do, on the desk in front of you, there's an envelope. In the envelope are some shapes, okay? I want you to open the envelope, and I want you to take out the blue rectangle, the orange rectangle, and the yellow rectangle. In this envelope, we've got a blue, an orange, and a yellow. All right. I want you to tell me how many different ways you can arrange them, and I want you to write them down using, like, for example, I've used a shortcut here. So B, O, Y, blue, orange, yellow. That's one option. All right? I want you to just see how many ways you can arrange them. All right. Winnie, if you've got an order for us, any order, just one of them. So we've got blue, orange, and yellow. Okay, so the first one, maybe, blue, orange, yellow. I'm wanting another option. Blue, yellow, and orange. Okay? Anyone got another one? Orange, yellow, blue, and another one? Blue, yellow, and another one? Yellow, orange, blue. Has anyone got one that we haven't got there? Are there any others? Are there any others? Can anyone make one that we haven't seen yet? O-B-Y. Yeah, we've got O-B-Y. There it is. Okay. Guys, that's all of them. All right? There are only 6. And the reason being is when you choose, now you got to choose which one are you going to put down first. How many choices have you got? You've got 3 choices. All right. How many choices have you now got if you put one of them down already? Only 2 choices. So 2 choices for the second position. And how many choices have you got for the third position? Actually, you haven't got any choices. There's only one option, yeah. So it's not really a choice. All right. And remember, the fundamental counting principle says we're going to multiply choices. Okay. And we get 6. All right. Now, 4 children run a race. How many different orders can they finish in? How many children of these 4 children, how many can we choose to come first? 4. How many can we choose to come second? 3. And third? And then 1. So how many different ways can these children finish? 24. All right. I've got 5 books. How many choices have I got for the first book on my shelf? 5. And then? 4. And then? And then 1. And so 5 times 4 times 3 times 2 times 1, 120. All right. This number, if we've got n things, all right, this idea of writing 5 times 4 times 3 times 2 times 1, we write like this. This does not mean 5, okay? That exclamation mark doesn't mean 5, all right? It just means 5 factorial, okay? So if we've got n objects, it's not n, it's n factorial. And you guys know this, but on your calculator, you've got a factorial button. So there it is, 5, shift, there it is up top there, factorial, and we get 120. These factorials get very, very big very, very quickly. If you try and work out 80 factorial, guys, what 80 factorial means is 80 times 79 times 78. What's happened? The number's too big for the calculator to store. All right, it's got more than 100 digits. Okay, it's a massive number, and that's why you get an error. Okay. All right, so the numbers get very big very quickly. All right, now, What I want you to do now, I want you to take out of your envelope, all right? I want you to take the blue, you've got the blue, the green, the blue, the orange, and the yellow, but I want you to take also 3 green shapes, one of each, just one rectangle, all right? One green rectangle, what's actually a square, a triangle, and a circle. Now, we want to arrange those things, but we want the green ones, the 3 green ones, to be next to each other. So what I'm going to ask you to do, you've got a little picture frame here on your desk. I want you to put the 3 green ones inside the picture frame. And then I want you to put your blue and your orange and your yellow outside the picture frame. Okay, so you should have 3. Put those green ones inside that frame. And then put your blue and your orange and next to in a line. All right, so your name is? Chris. Yeah, Chris, sorry. Chris has got, I'll tell you what Chris has got here. He's got his orange, then he's got his frame with the 3 green ones inside, then he's got a blue, and then he's got a yellow. What Mdu's got, he's got the blue, then he's got his frame with the green ones inside, then he's got a yellow, and then he's got an orange. Okay, and these are all correct, okay? Kolani has got a yellow, then the green, then the frame with the green ones inside, then an orange, and then a blue. Okay, right. So let's see if we can work out how many options there are. So if we think of the ones inside the frame as one object, then, am I right, we've got blue, orange, maybe frame, okay, I'm going to say frame, and yellow. So how many objects have we got if we count this as one? We've got 4. And how many ways can we arrange 4 things? In 4 factorial ways. Okay. All right. So we have 4 objects, all right? 4 objects which can be arranged in 4 factorial ways. Okay. But if we look at Chris's arrangement here, where he's got one specific arrangement, he's got blue, then yellow, then orange, and then the frame. Do you agree that the ones inside the frame he can mix around? Okay, and for this exact arrangement he's got, how many ways can he arrange those 3 things inside the frame? 3 factorial. And for any arrangement, so over here, here's a different one. This one goes blue, yellow, frame, orange. This one goes orange, yellow, blue, frame. This one goes yellow, frame, orange, blue. They're all different. All of you different in the room. Blue, orange, yellow, frame. Orange, blue, frame, yellow. Okay. Do you agree that for every single one of these 24, this 4 factorial is 24, all right, we can mix the ones inside the frame in 3 factorial, which is 6 ways. Okay. So actually you're going to have 24 times 6. And 24 times 6 is 144. You might ask me how I know that so easily. This is double 12, and this is half of 12. Okay, so 12 times 12, the double and the halving cancel each other out. Are you with me? This is 2 times 12, and this is a half times 12. If you use your brain, it gets better every time. 2 times a half is 1, so it's just 144. Okay, all right. Okay, so guys, that is a big conceptual idea, all right? And we'll look at another example. On my book, I've got 60, on my bookshelf, I've got 16 books. 6 of them are by one author called John Grisham, and 5 are by another author called Wilbur Smith. And I want to arrange these books. How many ways can I arrange them all together, all 16 books? 16 factorial, hala, hala. Okay, but now, what if I want to keep the ones that are by the same author together? It'll help me find them, okay? All right, so what we're going to do, we talked about a frame. I'm now talking about a rubber band. Okay, if we put a rubber band around these 6 books by John Grisham and these 5 books by Wilbur Smith, all right? And if we consider this as like one book, and this as one book. Now what you'll see outside here are another 5 books, because if we've got 16 and 6 and 5, 6 and 5 is 11, so there must be 5 that are just by other authors. Okay? If I consider these big books as one book, how many books have I got? 7. I've got 7 books. And notice I'm putting little quotation marks because it's not really a book. Okay. How many ways can we arrange the 7 books? 7 factorial. Okay. But for each one of those arrangements, like this, okay, these ones, how many ways can these ones be arranged inside the rubber band? 6 factorial. And these Wilbur Smith ones? 5 factorial. Okay. And so the final answer is going to be 7 factorial times 5 factorial times 6 factorial. Okay, it's going to be quite big. Okay, 7 factorial. Yeah, it's 5,040. I happen to know that 5 factorial is 120, and 6 factorial is 720. All right, yeah, so it's quite a big number. All right? When we write big numbers like this, it's helpful to write them with gaps. So we've got 435. Yeah, 435, 456. All right, but there, if you write it like that, it's actually easier to see. It's actually 435,456,000. Okay. All right, now the last thing we're going to look at before tea break, and this is all the background and the theory, and then we're going to solve some questions, okay? The last thing I want you to do is I want you to take from your envelope, just all the rectangles. What do we want to do? We want to ask you now, how many different patterns can we make using those? There's six shapes here. I'll tell you what we've got. A blue square, an orange square, a yellow square, and 3 green squares. Okay. How many different arrangements can we make? All right. Okay, now what you might notice is that all your green squares have got a small little number on. Okay. So they actually are all different. So how many ways can we arrange them if they're all different? It will be 6 factorial, because we've got 6 different things, and we can arrange 6 different things in that many ways. But now, so I want all of you to put them down in any order, just all in a row, please. Not in 2 rows, just in 1 row. Okay, you can put them in any order. So here we've got green, 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 orange, blue, orange, yellow. Here we've got green, orange, green, yellow, green, blue. Here we've got blue, orange, yellow, green, green, green. Here we've got blue, green, yellow, green, orange, green. Okay. Now, so there's loads of them around the room. There's actually 720 different possibilities, if they're all different. But if you look at your arrangement that's on the desk in front of you, and the one that I've gone for here is green, blue, yellow, green, orange, green. Do you agree that's a possible arrangement? Yes. Now, do you agree that if we turn these little green cards over, all right, then we're going to get exactly the same pattern, but now those cards are identical. Okay, and how many different ways can these 3 green cards be arranged in those positions? If we leave them in those positions, but we could have this one, we could go green 2, then green 1, then green 3, or we could swap these 2 around. Or we could, how many different ways can the green ones be arranged? 3 factorial, hala, hala. All right, so our answer will be 3 factorial times 2 big. All right, and I'm going to show you. Guys, here are all the different ones that look the same, okay? Because we've got green 2, blue, yellow, green, orange, green. Here we've got green, blue, yellow, green, orange, green. But do you see that there are 6 different ways that those green ones can be swapped around? So when we did 6 factorial, that answer is actually going to be, it's going to be 3 factorial times 2 big. All right. So in fact, our final answer is 3 factorial times 2 big. And the number of ways we can arrange 6 objects, if 3 of them are identical, is to take the total and divide by 3 factorial. Okay, and this actually now comes back down to 120. All right. Okay, and that's because that number is so small that actually when I look from here, it doesn't make any difference whether those ones can be swapped around and the pattern's the same. So we are counting by that many times too many, if that makes sense. Okay, we're going to just do 2 more examples of this, and then we're going to stop because we're going to have some tea. So I've got 3 green beads, 4 pink beads, a yellow bead, a black bead, and a blue bead. How many ways can I arrange them? Well, how many beads are there altogether? 3, 7, 8, 9, 10. If they were all different, it would be 10 factorial, wouldn't it? Okay, but the 3 green beads, so if I've just got one possible example where I've got a yellow bead, all right, I've got a black bead, and I've got my 3 green beads. Here's one, here's one, here's one, okay, and I've got my 4 pink beads. And I've got my 1 blue bead. So everyone see those are my 10 beads. So do you agree that if they were all different, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, there's an arrangement. And there are 10 factorial of those arrangements, if they were all different. But how many ways could I swap these green ones around? Just the green ones without changing the color, without changing the pattern. 3 factorial. So I must take my 10 factorial and I must divide by 3 factorial. How many ways can I swap the pink ones around? So I must also divide by 4 factorial. Okay, also on the bottom, on the underneath, I'm dividing. And what else must I divide by? No, so the yellow is only 1? Yeah, so in fact, that's it. There's my answer. Okay. All right, I'm not going to work it out. The last one. How many different arrangements can we make using all these letters? Okay, and I'm going to ask Ruth to give a chocolate to the person who can tell me the answer. You can give it in factorial form, okay? All right, so you can give me you don't have to give me the final calculated answer. Yes, over here. 9 factorial, Kolani. How much? And? Yeah, hala, okay, right, okay, there you go, right, guys, we're going to, if you turn, okay, that's the summary there. So if you've got n objects, I don't really like this as a formula, it's not provided, but if you've got n objects that are all together, A of them are identical, B are identical, and C are identical, then that's the number of ways you can arrange it. But I don't think it's helpful to give learners the formula. I think it's better for them to actually play around with the bits of paper.